Lake Taupo is New Zealand's largest lake, located in the central North Island. It's actually a massive volcanic caldera formed by a supervolcanic eruption around 26,500 years ago, one of the most powerful eruptions in Earth's recent history. The lake covers about 616 square kilometers and sits at an elevation of 357 meters above sea level. It's fed by numerous rivers and streams, with the Tongariro River being the most significant inflow, while the Waikato River is its only outflow, flowing north toward Hamilton and eventually reaching the Tasman Sea. Taupo is a popular destination for both locals and tourists, offering excellent trout fishing, particularly rainbow and brown trout, water sports, and scenic beauty. The town of Taupo on the lake's northeastern shore serves as a hub for activities like sailing, kayaking, and geothermal attractions. The area also features geothermal activity with hot springs and the famous Hookah Falls nearby. The lake is culturally significant to the Maori people, particularly the Ngāti Tufari Toa Iwi, who are the traditional guardians of the lake and surrounding area. Lake Taupo sits within one of the world's most active volcanic regions and has a fascinating geological story. The lake occupies a massive caldera created by the Oruanui eruption about 26,500 years ago. This was a supervolcanic eruption that ejected over 1,170 cubic kilometers of material, making it one of the largest volcanic events in the last 70,000 years. The eruption was so powerful it likely affected global climate and left ash deposits across much of the North Island. But that wasn't the end of the volcanic activity. The most recent major eruption occurred around 232 CE, about 1,800 years ago, in what's called the Taupo eruption. This event was smaller than Oruanui but still massive by normal standards, ejecting about 120 cubic kilometers of material. It created the current lake basin's configuration and was so violent that pumice from the eruption can still be found throughout the central North Island. Some historical accounts suggest this eruption may have been visible from as far away as China and Rome due to atmospheric effects. The lake sits within the Taupo volcanic zone, part of the Pacific Ring of Fire. This zone extends from Ruapehu in the south to White Island in the Bay of Plenty. The volcanic activity here is driven by the subduction of the Pacific Plate beneath the Australian Plate, creating conditions for explosive rhyolitic volcanism. Today, the Taupo caldera remains active but dormant. Scientists continuously monitor it for signs of unrest, including ground deformation, earthquake activity, and gas emissions. The geothermal features around the lake, hot springs, geysers, and fumaroles, are ongoing reminders of the magma chamber that still exists several kilometers below the surface. The geology beneath Lake Taupo is incredibly complex and reveals a long history of repeated volcanic catastrophes. The current caldera is actually built on top of older volcanic structures, creating a nested system of overlapping calderas that geologists call the Taupo Volcanic Center. Before the Oruanui eruption, there were at least 25 major explosive eruptions over the past 300,000 years, each capable of devastating large areas. The magma chamber underneath is estimated to be about 6 to 10 kilometers below the surface and contains a mix of crystal-rich mush and liquid magma. This chamber is what feeds the ongoing geothermal activity and poses the potential for future eruptions. The rock types here are predominantly rhyolite and dacite, highly silica-rich magmas that create extremely explosive eruptions. Unlike the more fluid basaltic volcanoes you might see in Hawaii, these silica-rich magmas are thick and gas-rich, leading to violent eruptions that can throw material high into the atmosphere and create pyroclastic flows that race across the landscape at hundreds of kilometers per hour. The lake floor itself tells an interesting story. It's not a simple bowl but has multiple basins created by different eruptions and subsequent collapses. The deepest point reaches about 186 meters, and the lake floor shows evidence of underwater geothermal vents and ongoing volcanic activity. Scientists have found evidence of at least 28 separate eruption episodes since the major Oruanui event. What makes Taupo particularly fascinating to volcanologists is that it represents a supervolcano, a volcanic system capable of producing eruptions with a volcanic explosivity index, VEI, of 8, the highest on the scale. The Oruanui eruption reached this level, ejecting enough material to bury all of New Zealand under several centimeters of ash. The geological record shows similar supervolcanic eruptions have occurred here roughly every 26,000 to 35,000 years, though predicting future activity remains extremely challenging. The geological evidence around Lake Taupo reveals the incredible violence and scale of past eruptions in remarkable detail. The ignimbrite deposits, welded ash flows, from the Oruanui eruption can be traced across thousands of square kilometers. These deposits are sometimes over 200 meters thick near the source and show a complex sequence of eruption phases, suggesting the event lasted weeks or months rather than being a single explosive moment. The eruption sequence itself tells a story of escalating destruction. It began with initial explosive phases that created massive ash columns reaching 35 to 45 kilometers into the atmosphere. As the eruption progressed, the magma chamber began to collapse, creating pyroclastic flows that traveled at speeds of 100 to 200 kilometers per hour and temperatures exceeding 800 degrees Celsius. These flows were so hot they welded together as they settled, creating the distinctive pink and gray ignimbrite rocks you can see in road cuts throughout the region today. Beneath the modern lake, drilling has revealed a complex stratigraphy of volcanic deposits interlayered with sediments from previous lakes. This shows that the Taupo region has repeatedly gone through cycles of catastrophic eruption, caldera formation, and gradual refilling with water. Some of these older eruptions were even larger than Oruanui. The Whakamaru eruption about 350,000 years ago may have been twice as large. The magma chemistry provides clues about what happens between eruptions. The magma chamber appears to operate as a complex system where new magma intrusions from depth mix with older, more evolved magma that's been sitting in the chamber for thousands of years. This mixing process can trigger eruptions, as the injection of hot, gas-rich magma into a cooler, crystal-rich chamber creates instability. Modern geophysical studies using techniques like seismic tomography and gravity measurements have mapped the current magma chamber system. It appears to be a sill-like body extending roughly 40 kilometers north-south and 25 kilometers east-west, with varying thickness. The chamber isn't a simple liquid magma pool but rather a complex mush of crystals, liquid magma, and gas bubbles, a state that could potentially be mobilized into an explosive eruption under the right conditions. The microscopic details of Taupo's volcanic deposits reveal even more about the catastrophic processes involved. Individual pumice clasts from the Oruanui eruption contain vesicles, gas bubbles, that preserve the moment of explosive decompression. These bubbles show that the magma contained enormous amounts of dissolved water and carbon dioxide, which turned to steam and gas during the eruption, driving the explosive expansion that shattered the magma into countless fragments. The mineral crystals within these rocks act like tiny time capsules. Quartz crystals show complex zoning patterns that record temperature and pressure changes over thousands of years before the eruption. Some crystals contain inclusions of the original magma, trapped at different stages of the magma chamber's evolution. These melt inclusions reveal that the pre-eruption magma was stored at temperatures around 750 to 850 degrees Celsius and contained up to 6% dissolved water by weight, creating a highly explosive mixture. The chemistry of different eruption layers shows how the magma chamber was stratified before the Oruanui eruption. The earliest erupted material came from the top of the chamber and was highly evolved, rich in silica and poor in iron and magnesium. As the eruption progressed, it tapped deeper, hotter, and less evolved magma, creating a chemical gradient that geologists can read like a vertical cross-section through the ancient magma chamber. Perhaps most remarkably, the speed of these eruptions defies imagination. Mass discharge rates during the climactic phases reached 10 to the power of 9 to 10 to the power of 10 kilograms per second, equivalent to emptying a volume the size of Auckland's Sky Tower every few seconds. The eruption columns reached heights where they interacted with the jet stream, distributing fine ash particles around the globe and likely causing measurable climate effects for several years. The post-eruption geology tells its own story of recovery and renewed volcanic activity. Lake sediment cores show that it took several thousand years for the ecosystem to fully recover from the Oruanui eruption. During this time, the empty caldera gradually filled with water, creating a lake that was initially much larger than today's Lake Taupo. Subsequent smaller eruptions have partially filled the caldera with new volcanic material, slowly reducing the lake's size and creating the complex underwater topography we see today. The heat flow measurements around Lake Taupo are extraordinary. Some areas record geothermal gradients of 200 to 300 degrees Celsius per kilometer compared to the global average of about 25 degrees Celsius per kilometer. This intense heat creates a complex hydrothermal system where meteoric water penetrates deep into the crust, gets superheated, and returns to the surface as hot springs and geysers. The circulation patterns of this hydrothermal system are so vigorous that they actually help cool the underlying magma chamber, potentially influencing the timing and style of future eruptions. The regional stress field adds another layer of complexity. The central North Island is being stretched and extended as part of the broader Pacific-Australian plate boundary zone. This extensional stress creates a network of active faults that can influence magma movement and eruption patterns. The Taupo fault belt, which runs through the lake, shows evidence of recent activity and may provide pathways for magma to reach the surface. Paleomagnetic studies of the volcanic rocks reveal that some eruptions were so intense they actually heated the surrounding rocks enough to reset their magnetic signatures. This provides a method for dating eruptions and understanding the thermal impact on the broader crust. Some deposits show evidence of being heated to over 600 degrees Celsius several kilometers from the eruption source. The volatile content of Taupo magmas, particularly water, carbon dioxide, sulfur, and chlorine, plays a crucial role in determining eruption style. Recent research has shown that the magma chamber acts as a giant pressure cooker, with dissolved gases accumulating over time until they reach critical concentrations. The triggering mechanisms for releasing this pressure remain poorly understood but may involve new magma injections, external stress changes from earthquakes, or gradual changes in the chamber's thermal structure. Perhaps most intriguingly, isotopic analysis of the volcanic rocks suggests that the magma sources have changed over time. The oldest eruptions show more influence from subducted oceanic crust, while more recent eruptions increasingly reflect melting of the continental crust itself. This evolution suggests that the volcanic system is literally eating its way through the New Zealand crust, creating an ever deeper and more complex magmatic architecture. Thanks for watching. Like and subscribe, and don't forget to explore more geological wonders on our channel.